feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional lesson here with Mr. Gaines as we continue our exploration of zeros and graphs of polynomials. So up to this point, we've really been focused on how we can factor and find zeros of polynomials. Now we are actually going to get a little bit further and focus on the graphs of these polynomials. So one of the things that we talked about in behavior of graphs, but another thing that we talk about is multiplicity of zeros. So in order to talk about multiplicity of zeros, I'm going to take a look at a graph of a polynomial here. So this is a graph of a polynomial, and we don't need to know the whole polynomial, but what we see is the linear factorization. So we see that the factors are x plus 3, x plus 1, which is squared, x minus 2, which is cubed, and x minus 4, which is squared. Notice that that gives us the zeros, negative 3 that goes with x plus 3, negative 1 that goes with x plus 1, 2 that goes with x minus 2, and 4 that goes with x minus 4. Right now, all we're going to focus on are the zeros. So what we can see here is that in some cases, the graph goes through the zero. In other cases, it bounces or touches the zero and then changes direction, makes that point a relative minimum or maximum, changes from increasing to decreasing on that point. What we may notice is the degree of the exponent correlates to whether the graph goes through a point or bounces off a point. So if I take a look at the exponents, at negative 1 and at 4, it's bouncing off of those points. They both have the exponent of 2 of those factors. At negative 3 and at 1, it's bouncing off, or it's passing through those points. They have different exponents, but those exponents are 1 and 3. If I change, let's say I change this to x minus 4 to the 4th power. Notice that the graph still bounces off at the 4. So really what's going on is the graph is passing through any point where the exponent is odd, and it is bouncing off of any point where the exponent is even. So we can write that formally that given p of x with factor x minus c to the nth power, assuming that c is a real number, if m, the exponent, is odd, the function will cross at the 0. If m is even, the function will bounce off or change direction at that 0, creating a relative maximum or minimum. So let's go ahead and see how that applies to some graphs. So if I take a look at problem number 6, this is the graph of f of x is shown to the right. State whether the degree of f of f is even or odd. So we need to come up with the degree for the function. So in order to do that, we have to take a look at the zeros. So remember that for the degree in this case, let's actually take a look at the end behavior. Let's go back a little bit before. The end behavior is up to the right and up to the left. So both of these two functions are going the same direction. Both of these two ends of the function are going the same direction. This only happens with even functions. So we can find out that f has an even degree based on its end behavior. It says use the graph to name the zeros of f and state whether their multiplicity is even or odd. Well, remember, zeros are the locations where the graph crosses the x-axis. So the graph crosses or intersects the x-axis, not just crosses, but intersects the x-axis in 3 locations. X equals negative 3, x equals 2, and x equals 5. So those are our 3 zeros, our 3 x-intercepts, our 3 solutions. It says state whether their multiplicity is even or odd, meaning does this 0 occur an even number of times or an odd number of times? If we look at x equals negative 3, it passes through negative 3. So that means the factor or that led to x equals negative 3 must occur an odd number of times. Once, 3 times, 5 times, so on. The same thing can be said true about the 0, x equals 5. The 0, x equals 2, at this location the graph changes direction. It is increasing to 2 and then decreasing on the other side. 2 is a relative maximum. So this only occurs when that multiplicity of that 0 is an even number, or if that factor x minus 2 was squared to the 4th power to the 6th power, and so on and so forth. So we know we have a polynomial with an even degree where x minus 3 occurred once, 3 times, 5 times, so on and so forth. Same for x equals 5. And x equals 2 either occurred 2, 4, 6, etc., an even number of times. So it says state the minimum possible degree for f. So the minimum possible degree, x equals negative 3 could have occurred once. X equals negative 2 could have occurred at minimum 2 times. And x equals 5 could have occurred at minimum 1 time. So at the minimum, we would have 4 linear factors. So the minimum possible degree is 4. So we know that we have at least this, the minimum degree for this function is a 4. This is at least x to the 4th power. Then in D, it says to list the domain in range. This is a little bit of a review question. Remember, domain refers to all of the x values. So the x values goes to the left and to the right forever. The range refers to all of the y or f of x values. In this case, there is a low point on the y. This is roughly negative 4, so f of x or y is greater than negative 4. So that's our domain in our range. Let's go ahead and let's take a look at 7. 7 is very similar. So if you feel like you are confident on this concept, go ahead and pause the video and see if you can answer the questions. We're going to go ahead and work through these questions just in case you need that help there. So it have g of x as a graph. It says state whether the degree of g is even or odd. Well, it's going down to the right and up to the left. So the polynomial is going in opposite directions here for the ends, which only happens for a function that has an odd degree. Then we have to find the zeros, find them, and state whether multiplicity is odd or even. Again, here we see 3 zeros. X equals negative 3. It passes through there. So this has an odd multiplicity, 1, 3, 5, so on and so forth. X equals negative 1. It passes through. So this has an odd multiplicity. X equals 2. It passes through there. So this has an odd multiplicity. So all of the factors that led to these zeros occurred an odd number of times. So the minimum possible degree would be 1, 1, and 1. So a minimum possible degree would be 3. The domain for this function is all real numbers. It goes to the left forever. It goes to the right forever. The range for this function is all real numbers. What we will find with odd degree polynomials is unless they have a domain restriction, the range is always going to be all real numbers because the ends go in opposite directions. What we'll find for even degreed polynomials is that the range will always be greater than or equal to some value because the ends go in the same direction. So this is how we have multiplicity of zeros start to come into play. It determines whether a graph is going to bounce or pass through a given value. Now, let's go ahead and take a look at 8. It says, for each of the following, state the degree of the function, then describe the end behavior and list the Y-intercept. So we need to find degree, we need to talk about the end behavior, and we need to list the Y-intercept. The degree of a function can be found by finding the multiplicity of each linear factor and adding that together. So for 8a, f of x, x plus 2, this linear factor occurs twice because it's squared. X minus 3, this linear factor occurs once because it's to the first power. So the degree for this function would be 3. The end behavior deals with the leading coefficient and the degree. The leading coefficient, if we were to multiply this all out, would be positive. When all the linear factors are fully factored, the leading coefficient should be listed out here. So it's going to be a positive value. So we know that to the right, this function is going to go up. It has an odd degree, so to the left, it's going to go down. To find the y-intercept, we have to do a little bit of work. So the y-intercept can be found by substituting 0 for x. Now, we have done that a lot when in standard form, where you can just take the constant. But when in factored form, like we see here, we do need to make sure we go through the process of multiplying. So if I put a 0 in for x, I'm going to get 2 squared times negative 3, which would end up being my y-intercept of negative 12. I can check this if I would like to by graphing. So if I graph this, x plus 2 quantity squared times x minus 3. Take a look at that graph. And I can see the end behavior is up to the right, down to the left. Can't see my y-intercept, but if I look at the table, I can see that that is negative 12. And I believe it does have a degree of 3 because it matches with my other two answers. Let's go ahead and take a look at B. B is a little bit different for the degree because this is not fully factored into linear factors. So if I wanted to look at this in linear factors, and you wouldn't necessarily have to, but I would be splitting this into a difference of 2 squares. This would end up being x squared minus 3i squared, which would end up giving us x minus root 3i times x plus root 3i times x minus 6. So the degree of this function would be the multiplicity of the linear factors all added together. So 1, 1, and 1, total of 3. I could also get this here by noticing that this is a linear factor, so it has a exponent of 1. This is a quadratic factor, so it has an exponent of 2. Those together would give me a degree of 3. Okay, so you can factor, but you don't have to if you can figure out the degree from the way that it was written. The end behavior, we know that this has a degree of 3, so the ends are going to go in opposite directions. This has a negative leading coefficient, so it's going to start by going down to the right. If it's going to go opposite directions, that means it's going to go up to the left. Then to find my end behavior, I would substitute in 0. So this would be negative, don't forget that negative out in front, 3 times negative 6. 3 times negative 6 would be negative 18 minus, times a negative 1 would be a positive 18. So the y-intercept for this function would end up being positive 18. I can check that again. So in my calculator, I can do negative x squared plus 3 times x minus 6. I can see my graph here. It doesn't give me a great picture, but I can zoom out and see that I do have the end behavior correct. I can look at the table and see my y-intercept is correct. So if you get this concept, go ahead and pause the video and see if you can complete C. Hopefully you had the chance to complete C. You should get that we have a degree of 4. So this has all linear factors. X plus 4 occurs twice, so 1, 2, 3, 4. The end behavior, because the leading coefficient is positive, it's going up to the right. It's even, so they go the same direction. This should be up and up. The y-intercept would be found, again, by substituting in 0. So you get 1 times 4 squared times a negative 3, which would be negative 48. So you should have a degree of 4. In behavior where it's going up both to the left and to the right, and the y-intercept of negative 40. Now let's go ahead and take a look at how we can combine these ideas to get into graphing polynomials. So in problem 9, it says graph each of the following functions using correct X-intercepts and Y-intercepts. So as I graph my function, the first thing that I'm going to do is I'm going to take a look at the degree of this function and the leading coefficient because I want to get in behavior. So I'm going to notice that this has a degree of 3. There are 3 linear factors, each of them occurring one time. It has a negative leading coefficient. So what I'm going to do in my graph is I'm going to go over here and I'm going to sketch into my graph. I'm going to sketch it to the right. I know this is going down because the negative coefficient, the coefficient is negative. I know it's going up to the left because the degree is 3, so it's going to go in opposite directions. Now I'm going to sketch my X-intercepts. It's already been factored for me, which is nice. I know that my X-intercepts are solutions to this equation. So they're going to be the zeros created by these factors. So x plus 5 is going to give me a factor of -5, or a 0 of -5. So there's my 0 at x equals -5. X plus 1, if I set that equal to 0, would give me a factor of -1. X minus 3 would give me a factor of +3. So I'm going to sketch each of those in. Now notice that each of these have a multiplicity of 1. So my graph is going to pass through each of those values. The last thing that I need to find is my y-intercept. So I can find that by substituting in, again, 0 for x. So this would be a -3 times 1 times 5. So 3 times 5 would be 15. Negative times negative would be positive. So I'd have a +15. Notice that my y-axis is not labeled here. So I'm just going to go ahead and I'm going to put a point on my graph and label this y-axis as 15. And now I can sketch my curve. So from 5, it's going to end up going up. Between 5 and 1, it's going to come down, and then it has to turn back around. Now, we're not exactly finding those relative maximums or minimum points. We're just graphing it using the correct x-intercepts and y-intercepts and making sure we have the right end behavior. So it's going through 5 and going up to the left. It's going to go through 1. It's going to go through my y-intercept. It's going to need to turn around and come back down to go through my next x-intercept at 3. And it's going to go finish going down to the right. So this does not have to be a perfect sketch. When we sketch it through, we know that polynomials are going to be curves. And so we want to make sure we're not using straight lines here. We want to make sure we're using curved lines to draw on this path. But all we really have to focus on is correct end behavior, going through the correct x-intercepts and hitting the correct y-intercept. After that, the relative maximums and minimums, we are not going to worry about finding those in Algebra 2. So x-intercepts are found from factors. Y-intercepts from setting the x's equal to 0. In behavior from the degree and leading coefficient, and then we can sketch in the curve. Let's go ahead and take a look at another example. In B, we have g of x, which has been factored for us, which is nice. So I can find my x-intercepts. My x-intercepts would come from x minus 1 as a factor, which would give me a +1. I set x minus 1 equal to 0 and solve to get +1. And notice that this factor x minus 1 has an exponent of 3. So it's going to pass through, it's going to go through 1. Now that's going to be different at 6. So x minus 6 would give me the 0, 6. So if I said x minus 6 equals to 0, so that would be at 1, 2, 3, 4, 5, 6 here. It's going to bounce off of 6. So when it comes to 6, if it's coming from above, 6 is going to be a relative maximum, or 6 is going to be a relative minimum. So it's not going to pass through, it's going to bounce off of that value. Sorry, I forgot initially to talk about the degree. The degree of this function would be 5. So x minus 3, that factor occurs 3 times. X minus 2, that factor occurs twice. So we have a total of 5 linear factors. The leading coefficient is positive. So to the right, this function would go up. To the left, this function would go down. I do need to make sure I include my y-intercept, which would be g of 0, which is -1 cubed times negative 6 squared. If you needed to do that in your calculator, you would come up with a negative 36. So I'm going to put a point on my y-intercept or y-axis and call this negative 36. So my graph should finish going down to the right. Sorry, down to the left. So it's going to go down to the left. It's going to come up through 1. So it goes through 1. We said it bounces off 6. So I'm going to bring it back down to 6. I'm going to bounce off 6. And I'm going to continue going up to the right. So this would be my graph for g of x. It has the in behavior of up to the right, down to the left. It passes through my y-intercept of negative 6, through my x-intercept of 1, and bounces off my x-intercept of positive 6. Let's take a look at one more. Actually, let's go ahead and at this point, let's see if you can pause the video and do C. Hopefully you got a chance to work on C. So if we took here and we took a look at the degree, let's go ahead and go through this. The degree would be 4. Along with the degree of 4, it's going to have a leading coefficient that is positive. So we know that to the right, it's going to go up because the leading coefficient is positive. To the left, it's going to do the same thing because it is an even degree. And then we can go ahead and start to sketch in the different pieces for the graph. So we have an x-intercept here of negative 1. We have an x-intercept here of negative 4. We have an x-intercept of positive 3. It is going to pass through, because the multiplicity, it's going to pass through negative 1. It's going to bounce off negative 4. And it's going to pass through positive 3. Now I need to include my y-intercept. So my y-intercept again can be found by substituting in 0 for x. So I would have 1 times 4 squared times negative 3. And this would end up being a negative 48. So I'm going to go ahead and put a point on my y-axis and call this point negative 48. Now I can sketch in my curve. Again, it's going to bounce off of 4. It needs to end up going up to the left. So I'm going to draw this curve in here. It's going to bounce off of 4. It's going to go up to the left. It's going to turn around. It's going to pass through 1. It's going to continue going down. It's going to pass through my y-intercept. It's going to turn back around. It's going to go up and pass through positive 3. It's going to finish going up to the right. So this is what our graph looks like. Again, we're not worried about finding exactly where those relative maximums and minimums are. As long as you get the right x-intercepts, whether it's passing through or bouncing, you have that correct. You have the right y-intercept, and then you have the right in behavior. That's what we're looking for. Let's take a look at one more example here where this is already factored for us. H of x. So in h of x, again, we want to find the degree. Now notice that we have some imaginary units here. They still count as linear factors. So the degree for this function would be a total of 4. Because we have x plus 1 that's squared, and then x minus I and x plus I. The leading coefficient is negative, so this is going to go down to the right. It's going to go down to the left. My x-intercept, and then notice I said x-intercept, would be 1. I'd only have 1, or sorry, a negative 1. I'd only have one x-intercept. The zeros that would come from this, x equals I and x equals negative I, are imaginary zeros. So they would not show up on our graph. Now, if I want to find the y-intercept, I do need to substitute in 0. So I would have negative 1 times negative I times positive I. Remember, I times I is I squared. So this is basically negative 1 times negative I squared. I squared is negative 1. So I have negative 1 times a negative 1, which all of this comes out to be negative 1. So now I can go ahead and sketch my graph. So I know my graph is going to go down to the right and down to the left. It's going to bounce off of this point at -1. It's going to pass through my y-intercept of -1. And it's going to look something like this. Okay. Again, it's not an exact replication of our graph. It's a sketch including the correct x-intercepts, y-intercepts, and in behavior. Now let's take a look at a little bit more complicated of a graph in problem 10. So it says graph each of the following functions using the correct x-intercepts and y-intercepts. Now in this case, we're in standard form. Yes, I could type this into my calculator and just sketch the graph. You're going to, on occasion, have to show an algebraic support process for getting to that graph. So in order to do that, what we need to do is we need to factor the function. If we have factors, we can go ahead and graph the x, y intercepts and the in behavior. Now, what I would do here is I would go ahead and start with the y-intercept. The y-intercept for this function would be fairly easy. It's in standard form, so if I substitute in 0, the y-intercept is going to be -9. So we saw this with quadratics, and it's true about polynomials. Polynomials in standard form, the constant is the y-intercept. We can see that it's a degree of 4 and a positive leading coefficient, so I'm not even going to write it down. I'm just going to go ahead and get the in behavior. Positive leading coefficient means we go up to the right. Degree of 4 means that both ends are going to go the same direction. Now, if I want to graph this, I need to know what my x-intercepts are. I need to know my zeros, my solutions, my roots. So what I'm going to do here is I'm going to factor this. This is a quartic trinomial. So I'm going to try to factor this into two binomials. X squared and x squared would be my first term because those would multiply together to give me x to the 4th. And then through the distribution, we want them to give me a positive 8x squared. Factors of -9, we know that one has to be negative, one has to be positive. We believe that -1 and +9 would be the correct factor. So this would give me a -1x squared, 9x squared. If you add those together, that does give you 8x squared. So I have x squared minus 1 and x squared plus 9. Now I'm going to go ahead and factor this further. The first part is a difference of 2 squares, so I'm going to come back to that. The second part is a sum of 2 squares. So I'm going to turn this into a difference by using I squared. Remember, I squared is -1, so I'm going to change a positive 9 into minus 9i squared. The reason I do that is because now I can factor using the difference of 2 squares and conjugates. So x plus 1 and x minus 1 are factors. X plus 3i and x minus 3i are factors. Now, if I noticed I had imaginary solutions, if my goal was just to graph, I could kind of ignore factoring this sum of 2 squares because we know that's going to be imaginary zeros. We are going to have some problems that say to completely factor and then graph. So we do need to make sure we can get all the way down to x plus 3i and x minus 3i. When it comes time for graphing, the only two things I'm worried about here are the x plus 1 and the x minus 1, which give me 2 x-intercepts. Both of these have a multiplicity of 1, which is an odd number, which allows the graph to pass through those values. So I'm sketching in my curve, making sure I hit my y-axis. I pass through my x-intercepts, and I have the correct end behavior. Now, if I were to check this graph, if I were to type this into my calculator, x to the 4th plus 8x squared minus 9, and take a look at that graph, I would see that I have a pretty close representation of what this graph looks like. So what we want to do is we want to find the in behavior. We want to find the y-intercept. We want to find the x-intercepts. If we don't have the x-intercepts given to us in factors, we need to factor that equation to find those x-intercepts. Then we can graph those and finish the equation. This is a good place to stop for today. So when we return, or when we get another video, we're going to continue working on graphing functions, polynomials in standard form. And then we're going to look at some applications of polynomials. As always, thank you guys for tuning in, and I'll see you soon.